Okay. Ready to... Okay, we can start now. It's the time before the spring break, so we're going to have discussion, and we better make it a lively one. Some of the people have already left for the break, including two of the people who are supposed to present on the discussion today. It's a little bit of my fault because we did not warn them on time. So what we're going to do is we'll have Shishin present quite a bit of protein research, which actually very much covers the things that we have studied so far. And then I'm going to show some cool things about DNA assembly and similar type of structures made by biological interactions. And feel free to really make this a discussion. So this is not a lecture. Now, something that I had in mind to tell you with regards to the questions that I had been receiving about the homeworks regarding the electrostatic interactions. Pay attention that the electrostatic interactions in the formulas that I have given you are typically presented in the dimension of particles or ions per cubic meter. They're not concentrations in moles. So when you do concentrations, make sure that you convert the moles to particles per cubic meter. Otherwise, you get some weird results which are too large or too small. So that's one about the electrostatic interactions. Okay, without too much further discussion, let's give the floor to Shishin.
Okay, thank you. Good evening. My name is Shishin, and I'm working on my PhD in food science and chemical engineering. And we have learned a lot about colloidal interactions in the lectures. And today I'd like to just apply these interaction concepts to analyze how we can use these interactions for our life. And in this case, we're going to discuss the stability of casein micelles in the milk. So before going anywhere, we have to know our system. Most of you have known that milk is basically aqueous dispersion. Most of them are water. And also milk has fat, protein, and some sugar and minerals. And protein is the major components determining milk stability. And 80 of proteins are casein, and the rest of 20 are whey proteins. Casein has 4 types: alpha, beta, kappa, and gamma. And whey protein is very stable, it's very water soluble, and it's depleted during cheese making. And because it's depleted from cheese industry, so it's basically a big byproduct. And lots of research has been done on whey protein, trying to make it into value-added products such as thickening agents, gelling agents, or foaming agents. But what determines casein stability is basically casein. What determines milk stability is casein. So we want to know how casein exists in milk. But unfortunately, up to today, there's still no conclusive words on how casein is behaved in milk. This graph shows the general concept idea how casein behaves in the milk. Basically, caseins are called casein micelles, but they are not strict micelles because, as you can see, they are consist of small submicelles. So if they are not purely hydrophilic shell and hydrophobic core, and basically they have lots of submicelles. And these submicelles are connected by some calcium phosphates, in which case there are blue dots on the figure. And there's maybe some hydrophobic interactions connecting these submicelles too. And it's believed that kappa casein is rich on the outer surface. And as you can see on the right-hand side of small figure, This is the structure of submicelles on the outer surface. And as you can see, it has a very small amount of hairy layers on the outside. And cap casing is enriched in outside areas of these submicelles. And as far as the size is concerned, and casing micelles size is log normal distributed, and it could be as small as 30 nanometers and as big as 600 nanometers. And the average size is about 200 nanometers in diameter. And each of the submicelles has around 15 to 25 molecules, protein molecules, and the size is about 10 to 20 nanometers. And the thickness of this hairy layer is about 5 to 10 nanometers. So as you can think about, look at this figure and say, it looks pretty similar to lattice particles graphed as a polymer layer. So you can think about it as hard sphere with polymer brush on the surface. So we have a strong steric interaction. And because this steric interaction, it makes milk very stable. So even though you spray dry it or freeze it, the structure of casing micelle can still be maintained. And on the other hand, if we change solvent conditions, for example, if we lower the pH, and this is actually done in cheese making. In this case, it's cottage cheese. And it's also done in yogurt making process. Because in this case, the pH of the whole system is decreased from condition of milk, which is about 6.7, to the isoelectric point of the casing, which is about 4.6. So as pH is lowered, cap casing layer will collapse, and casing micelle will start to aggregate. And as I said, you can think about casing micelle as hard sphere with a brush on the surface. So there might be some way to cleave this brush, and if brush is cleaved, steric interaction no longer exists, and then casing micelle will aggregate too. And this idea is actually done in cheese making process. Oh, before going into that, I have something to show. So this graph is actually the net charge of cap casing that I have calculated. As you can see, the horizontal line is standing for zero charge, and at pH about 4.6, which is Pi of the casing, the charge is 0. And at pH lower than Pi, protein is positively charged. And at pH greater than Pi, protein is negatively charged. And higher pH, more net negatively charged. So as I said, in cheese making process, there's a process called renneting. What renneting does is some enzymes, in this case it's called chymosin, from calf's stomach. And this enzyme can cleave cap casing on the surface. And because if cap casing no longer exists, and then the stability of the casing micelle will no longer be maintained. So we know what makes milk stable and what makes milk unstable. So we want to go into how to describe interactions between casing micelles. And as universal van der Waals forces exist between any objects. So if we say we have two particles separated by a distance h, and you can calculate van der Waals interactions as a function of Helmholtz constant times some more complex expression between of function of h and a. So, and you can actually find this expression in class notes. So if we know the Helmholtz constant for our system, and we can predict what the van der Waals interaction is as a function of separation. And literature shows most of protein has have omega constant between 1 to 3 kT. And for one case of whey protein, which is beta-lactoglobulin, the omega constant is about 5 kT. For casein micelles, it's about 6 times less dense than beta-lactoglobulin. So the authors just say, okay, why don't I just treat omega constant as 1 kT? And another forces in DLVO is...
I have a question here.
Yes.
Now, are these theoretical or experimental forces?
Theoretical experimental forces.
Are these Hamaker constants determined theoretically or
No,
experimentally?
this Hamaker constant was calculated by some polarability of beta-lactoglobulin and some specific wave frequency, I guess.
Right.
And it was calculated. It's not experimental. So
Right.
it's theoretically.
I have to point out, however, that the experimental constant usually comes to be much larger than this one.
Okay.
And the reason for this is because for experimental Hamaker constants, actually you bundle forces which are not described by the van der Waals interaction, like hydration and hydrophobic forces.
Right.
So these are theoretical forces actually.
Yeah.
Okay.
So another DLVO force is electrostatic interactions, and actually this expression is from Cosmos. So we have electrostatic interaction expressed as radius of the spheres and relative permeability and surface tension, and also exponential function of separation divided by Debye length. For milk, the ionic concentration is about 0.08 molar. So we can estimate the Debye length to be about 1 nanometer. At neutral pH, the surface potential of milk is about -8 millivolts. And as pH gets closer to PI, which is 4.6 again, and there's no charge exists on the protein surface, so surface tension will become 0. And so far we know the two forces for DLVO, but we know protein is not strict, cannot be completely described by DLVO. And I talked earlier, we have polymer surface on casein micelles. So we have steric interaction. So next step is how to quantify steric interaction. And this is a scheme. It's not real picture of casein micelles. So it looks like it has hair on the outside. So it looks a little bit ugly. So I replaced that by a nicer one. So you can describe it as a system as two spheres with a layer of casein with a thickness of h. And this h is determined by number of polymer segments n times the segment length b, and it also determined by the effective excluded volume, which is v of EFF, and the density of surface coverage, which is theta here. And the effective excluded volume has two parts. The first part is the I believe it's effective volume of a sigma, which is mu here, and the other part comes from the pH effects. So the other expressed mu as 1 minus 2 times chi. Chi here is Florey-Huggins parameter. So for chi greater than 0.5, it's a best solvent. So for chi less than 0.5, it's greater than 0. Mu is greater than 0, so you can say it's a good solvent. and alpha is determined by the dissociation constant and pH. And so if we know pH and we know Ka, we can estimate alpha, and we can calculate height of the casing brush by knowing the structure of this brush, and the sequence of cable casing can be actually learned from literature. And the authors actually did calculate the brush height, and this graph shows the height of casing brush relative to the height at pH 7.0, which is close to the pH of milk. So as you can see, as pH decreases, and polymer brush height decreases too. And what surprised me was up to pH 4.6, Chi has had almost no effect. I don't know why, because if you think about it, if you think about polymers in a good solvent, it should have bigger size than in a bad solvent. I don't know why this happened. And if we know the brush height, and we can express the steric interaction as function of brush height. So if you look at this chart, for a separation greater than twice the brush height, the polymer brush are not touching each other, so there's no steric interaction. But if the separation is smaller than 0, and then basically casing micelles cannot be pressed further. So the steric interaction is basically infinity. And the separation between 0 and twice the brush height, it's a function of brush height, separation, and density of coverage. You can find specific expression in original paper. So far we know the van der Waals forces, the electrostatic interaction and steric interaction. And the authors calculate these three forces and expressed here. As you can see, brush repulsion, which results in steric interaction, is repulsive forces. And at the separation up to close to 5 nanometers, it's much greater than electrostatic interaction and van der Waals forces. So basically, at this separation, the net force is repulsive, so the particles are not aggregating. So this is why it makes milk so stable. And the author thought, electrostatic interaction is much smaller than steric interaction. So they just add steric interaction and van der Waals force together. And they calculated the net force. I believe the y-axis should be total interaction energy divided by kT, the times kT. So the authors calculate the total interaction at different pH values. As you can see, at pH greater than 5.0, the net force is all repulsive, so casing micelles are still stable. But at pH smaller than 5.0, the attractive forces start to come into picture. And actually at pH 4.6, at Pi, the force is almost attractive. And as Dr. Velev said, for protein system, we have second virial coefficient that can characterize the interactions between proteins. And this coefficient is actually can be correlated to the total energy of interaction by this expression. So for B2 greater than 0, the net force is repulsive, so it's stable. And what the other said was, generally, if B2 is smaller than -6, suspension starts to behave unstable. So the others just substitute the total interaction in the expression and calculated second virial coefficients. And this figure shows second virial coefficient as function of pH at different percentage of kappa casing on the surface. At 0% of 0% here means 0% of kappa casing being cleaved. So it's the original identity of the milk. So as you can see, the red line stands for a B2 minus B2 value around -6. And if it's smaller than -6, and casing micelles become unstable. So it's about the isoelectric point of milk. But if the amount of casing is cleaved further and further, as you can see, 20%, 50%, 60%, and the coagulation happens at higher pH. So far, this prediction described how milk stability is changed during acidification and reducing process. As you think if pH decreases, the milk becomes unstable, and as amount of kappa casing is cleaved from surface, and kappa casing micelles become unstable too. But because casing micelles are not very stable at some specific conditions, so I thought following points might have to be considered. The first one that I thought was pH effects, because literature shows at pH other than neutral pH, casing micelle structure is going to change, specifically at pH closer to isoelectric point. Calcium phosphate will dissociate from casing micelles, so will individual casing molecules. So if this case is true, and then the particle size is going to change, and what we have discussed might not be very applicable to different pH values. And also what the literature shows is casing micelles will become bigger at a lower pH. And the other factor that I thought was because what we discussed so far is just two particles. And in the milk, there might exist more than two particles, so other particles might affect the interaction between two particles too. And this function is called many body effects. And there is a function called pair distribution function that can be included in calculating total interactions. And the other one was, I thought electrostatic interactions at some point has to come into picture, because if we say as pH decreases, kappa casing layer thickness will decrease. So even though we say electrostatic interaction only happens at 1 nanometer, it might have some effect too. And actually, if we look at the next figure, this figure shows how the relative viscosity of the milk can be correlated to the interaction between particles. And the solid line here is the relative viscosity predicted by the model. So as you can see, it has some deviation from the actual data. So if everything is perfect, and the dashed line should predict what interaction can determine the relative viscosity. So as you can see, this is actual data. So at 80% of cleavage, and the viscosity starts to become very, very high, which in this case, the coagulation of casing micelle happens. So the model actually predicts the coagulation happens at smaller amount of cleavage, which means it's less stable than what we thought. So we say maybe at this case, at cleavage greater than 40% or 50%, the electrostatic interaction might come into picture, and it increases the stability of the system. So that means the stability happens at higher percentage of cleavage. So to summary, the predictions are possible for some specific conditions, even though for complex biosystems. And what interests me was because if we know this interaction between particles, we can correlate this to the rheological properties. In this case, I show the expression between storage modulars that's related to second derivative of interaction with respect to separation. And also to make our model more perfect, or to make our prediction more perfect, we have to consider more factors.
Okay.
What's capital N?
Capital N is number of crosslinks in a colloidal system.
Okay.
That's the last slide, right?
Yeah, this does.
Okay, I have questions, but maybe before me. Okay, let me start with my question while the others are thinking about theirs. Now, you eventually show that it can aggregate when you cleave the brushes,
Right.
or when you change the pH.
Mm-hmm.
Now, why do then people usually make cheese by cleaving rather than by just changing pH?
I think it has
I
something.
think you can just add some acid and it's going to make cheese without renating, right?
Right. It's depending on cheese type. Actually, cottage cheese is made by just changing the pH. But for these cheeses made by renating, I think it's more related to one is it's firmer, I guess, and the other two is related to the flavor.
Uh-huh.
So you want a cheese that has right flavor, and which might not be achieved by just lowering pH.
So cottage cheese then should be acidic in taste, is it? Or?
It's
Well,
funny.
No, it's not.
It's not.
Tartaric
You're
acid
funny,
or
it's
something.
funny
It just
cottage cheese.
What's
In Indian dishes, they have a
Uh-huh.
Something like tofu.
tofu
Uh-huh.
kind of thing. That's equivalent to a cottage cheese. You add some lime to it and you.
Well, why do that's kind of
So
strange.
that's like lowering the pH.
Uh-huh.
So you add some lime to it.
Lime is what?
Add some lemon to it.
Lemon.
Lemon
okay.
juice to it.
Uh-huh.
So
Uh-huh.
it lowers the pH.
Hmm.
And then you just like take a cloth and you remove the part and let the water dry out.
You should try that cheese pie for your style.
Yeah, maybe.
Anyway, other questions? Daniel seems to have a question or not?
Well, I was just wondering, like in the old days, the milk would separate.
If you just let it stay outside.
Yeah. And I mean, is this, are we getting aggregation, coagulation there from some sort of change in the system, or is that just because it's oversaturated?
Maybe there's some like microbial concerns, because if you put it in the system, it's not pasteurized.
Right, unpasteurized milk.
Right.
So the microbes start eating the
Right.
proteins and cleave them, and you don't have steric repulsion and it separates.
Could be.
So it's like curd.
But
What
Uh-huh.
happens when you make yogurt?
Yeah, I guess, that's, I don't know whether it's because there was steric repulsion or because you have the microbes there, but
yeah, there is actually lactic acid bacteria that's gonna eat up the sugar in the milk and at the meantime low in pH.
yeah,
And that's
maybe the
what.
pH changes also.
Right.
Does yogurt have
What
dissolved
happens if you
gases
increase
in
the
it?
pH?
Huh?
What happens if you increase the pH? You go above
Basic?
Go over pH.
I know what happens if you actually increase the pH above 7, and this is that you're going to spit it out because it's going to taste like soap.
Right.
So any food should be below pH 7, right?
Well, maybe not.
Otherwise it will be
Yeah.
stable, but I don't think foods
But
are...
most foods are
Around
lower
five
than
point.
pH 7.
Yeah, typically food above pH 7 would taste like soap.
And at pH, higher pH,
Stick to your tongue.
at higher pH, it's not microbial safe too.
Not microbial safe.
It's more dangerous to have some microbial concerns.
Could-
Just any.
Could you just review for me? How do you cleave the chitin, the
Kappa casing.
the kappa casing? Yeah.
It's an enzyme. Basically, kappa casing has about 169 amino acids, and 60 something of them are sticking outside. This part is very soluble, and the rest of kappa casing is not that soluble, so it's embedded in casing micelles.
Uh-huh.
And the enzyme recognizes the sequence between 105 and 106. So it's the lock and key.
Okay. Oh, so you had the enzyme. Please.
You have to have enzyme to cleave that.
Oh. Yes.
In the enzyme, again, the message here, which was relevant to what we were speaking the last time and what I'm going to show now, the enzyme exactly cleaves the same place on the protein because it recognizes kind of lock and key where it fits in the exact. There is only a specific sequence of amino acids which fits onto the enzyme cleaving kind of active site.
Is there a type of cheese called Rennie cheese?
I'm sorry.
Is there a type of cheese called Rennie?
Yeah, actually, I have a
Rennet.
question about that. There was a word. We're gonna go back a few slides.
Renneting.
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 Rennet. Rennet cheese.
Renneting.
What does that mean?
That's when you add
That's when
acid.
you add.
Well, actually, the whole stuff taken from calf stomach is called rennin.
Okay.
R-E-N-I-N.
The enzyme.
R-E-N-N-I. Huh?
This is the enzyme or what?
Well, it's a mixture. It's the old style cheese making, so it's taken basically from calf stomach.
You have to kill the cow
And
to
this-
get it.
No, you can take from live, I guess. And then
I'm never eating cheese again.
no, it's fine. And then I think
He's the one
I think that's what we need
inside
to
the
come
cow.
up.
Somebody sticks their arm down the
You got killed
Do
it.
you have a
They
question?
cannot.
Or you're just
Crucial.
sick?
It's trying to.
It's
He's trying to figure out how this is actually done.
end of the week.
I don't know too. I'm just guessing it's.
Not your job, yeah.
Okay. Any other questions? Now, there is the story of the KT. I have had quite a bit of arguments actually with my advisors in Delaware when I was working on proteins. And the story about KT is like that. If you measure it experimentally, you obtain high KT on the order of, let's say, 10 KT. When I say sorry, KT, Hamaker constant. So the Hamaker constant that you would obtain if you just measure it experimentally would be about 10. And then when the theoreticians sit down and calculate the Hamaker constant, they obtain a Hamaker constant of 3 to 5. And of course, about half. So the question is, what happens? Is the Hamaker constant that's calculated or that which is measured, right? And right now, the current understanding is that the experimental Hamaker constant includes all those complex interactions, which we don't know quite well yet. So proteins would stick, but they would stick in a way complementarily. They wouldn't kind of, let's say, stick in any configuration, but they would adjust themselves. So they stick very well. So their shapes match. And this is and then when you model this, of course, you can't model it to that extent. So this is the reason why experimentally the Hamaker constant that you measure kind of encompasses the forces that you can take into account. So this is an ongoing argument, what would be the right Hamaker constant to use in such systems.
Right. That's all.
So, okay, do you have any other questions? Okay, so let me then, I'm going to show a few things about DNA now. For our distance education students, we're going to actually, what we're going to do, we're going to get the two presentations together and make them downloadable from the web page. So you'll be able, in a day or two, you'll be able to download this slides that Shishin showed, and that I'm going to show.
Okay, I got to close this first. I
Let's
guess.
close it.
Alright.
Yeah, close PowerPoint. Okay. Okay. I'm going to show a few interesting things, but again, the idea is to have a discussion. So don't hesitate to stop me and ask questions, rather than trying to turn this again into the lectures that I'm usually giving. And there are many interesting, sometimes controversial issues when you reach those, when you study those structures. Before I begin, just the first slide is again crash course in DNA and how it works and what it is made of. I'm sure that you have studied this. Again, what I have done here is I have extracted what's important from colloidal viewpoint. Yeah, okay, but then, okay, it's been a long fight with that device. So you know that DNA is eventually this double spiral where you have the two sides of the spiral zipped in a way to each other. Now there are 4 elements, actually 5, but one of them is actually a substitute for the RNA of these groups which binds to each other in what type of interaction. It's not exactly, you wouldn't call it lock and key, but it's very strongly specific. So this is the equivalent of a lock and key type of interaction. So you have the adenosine thymidine groups locking to each other, and then we have the guanosine cytidine groups also locking to each other. Out of those, this one is about 1/3 stronger. Okay, about 50% stronger. And that would be because of what? Yeah, essentially this one forms 3 hydrogen bonds, and this one forms only 2 hydrogen bonds. Now, why doesn't this one lock onto that one, for example? The reason is that it's not only that it makes hydrogen bonds, but they match each other so well that the hydrogen bonds are optimal only when you have these two groups facing each other. And of course, in reality, it doesn't look as nice as that. I mean, you have also the spherical kind of considerations, but you can see how exactly they match each other very nicely and lock on. Now, why are these structures useful for research? Now, there are 2 views to that. I mean, of course, the first is pragmatical view. You can design any type of DNA, and then it's very easy to make it. These days, you have this DNA synthesizing machine. So if you just program the machine, it's going to make the DNA strands for you, and you can take it out. There is lots of interest in this area. Some of that interest is, in my view, a little bit hyped. And it's a little bit hyped because the DNA is the origin, of course, of the genetic information in life. So people get specifically excited when it comes to DNA. Now, many of the things that you can make with DNA are very expensive. But on the other side, you can really do a variety of cute things. So what I'm going to do is I'm going to show just some selection of such cute things that you can make with DNA. There is this guy Ned Seaman from New York University who presented a seminar in the Department of Chemistry a couple of years ago. Did you attend that seminar or you missed it?
We're first years.
Oh, okay. Well, I mean, you can hope that he obviously has some friends here, so he's going to possibly come again.
Was that last year, or is it?
This was when you were just starting.
Okay. Sounds really cool.
Right. I don't think, however, that you visited the seminar, so I'm going to just give you the basics of what he does. Now, imagine that you take DNA and you design, let's say, 4 strands. So these strands match each other in only one specific configuration. It is this one. What you do is you just synthesize these DNA molecules on the machine, and then mix them in the solution, and then after you mix them, you suddenly find that this DNA is assembled in this kind of cross-like assembly. And he claims that he can, with some more engineering of the DNA strands, how they match, he can make structures which can be as complex as this one.
So that's a model he hasn't observed.
I'll show you some of the things he has observed, but he claims that he can make something like that if he wants to, or cubes or something, structures like that. And they self-assemble. It's very simple. Once you synthesize them, you just put them in solution, leave them for a while, a day or two, and then you just find the structures being self-assembled. And he has this interesting, again, we're having a little bit fun now before the break and so on. He has a very interesting talk which shows the way he explains why he makes the structures like that. He obviously also likes history, and he has been to Europe. So he has found some interesting, a little bit kind of like, well, how to say, gloomy or strange structures which are made by human bones and skulls in monasteries and catacombs and so on. So in the catacombs you can find eventually human hulls stacked, or in some monasteries you can find some actually, let's say, light fixtures which are made of human bones. And he says like that, now nature has designed this for something else, but you can use it as a building material for the structures, for artificial structures that you like. You can make arrays, you can make different things. So in a way what he does with DNA is something similar, because DNA was designed to carry genetic information. But with some engineering you can use this natural molecule to make some structures which you can't make otherwise. Now this is a little bit weird in the sense of what you can do out of that, but everybody is interested in different types of periodic structures, especially if you can attach some electrical functionality to that. So this is a real example of how it looks like and how he designs them. So you can take DNA strands which actually have this cross-link here, and you can design them so they match in this specific pattern. And then you can also attach a nanoparticle to one of those strands. And you just put them in your test tube, leave them for a while. And after this, you observe this with atomic force microscopy, and this is what you see. Now, the periodicity of this structure is so small that you can't really see, of course, the DNA strands themselves, but you can very much follow the periodicity which is imparted by the nanoparticles.
You have to do this in an aqueous regime. You can't take it out afterwards.
Oh, sure, it's an aqueous solution. Well, I don't know what happens if you try to take it out, actually. But typically DNA would exist in aqueous. I mean, it's going to shrink and kind of very much whatever you take out of it.
Yeah, that's really small.
It's really small, but again, this is a kind of self-weaving structure with nanoparticles on the surface, and these nanoparticles are organized in these arrays and so on. In principle, you can think about molecular electronics if you like. If you find a way of storing a bit of information, on each particle here, you can think about what is the density of. So essentially you store a bit of information with a density of 27 nanometers. The pitch of 27 nanometers, and so this can be really dense way to store information. Now, whether this is practical, financially, or technically is another matter.
What's the current pitch for hard disk and stuff like that?
It goes to hundreds of nanometers per domain, so you would like to shrink this down. Now, the point is that you can, now this is a bit visionary, because how are you going to exactly write the bit of information there? But in principle, you can make those nice, cute arrays and so on. And of course, you would like to use biological structures in order to assemble nanoparticles. And this is fundamental. So try to understand that. I mean, it looks a bit complex. Actually, it's very simple. What you see here is an experiment made by Chad Merkin, a guy at Northwestern University, who has attached DNA strands to particles by using sulfide chemistry. And then you have another DNA strand which can or cannot match the two strands here. So eventually you have these particles floating in the solution. Actually, and then if you put this third strand kind of flips and bridges them, zips them together. You can deduct the strength of the binding by actually heating this up. Now, if you remember from my course, DNA there is really a couple of effects. One is entropic, and the other one is enthalpic. And these effects are dependent on temperature in a way. So actually, the entropic effect of this connection takes place at a higher temperature, but this temperature is about something that you can easily make. So the temperature at which they disassemble actually tells you how strong is the binding. The stronger the binding, the higher the temperature. So if you take just these two particles with DNA strands, nothing happens. I mean, there is no temperature here because there is no interaction even. So they are always disassembled. Now if you take these particles and you put in a strand which does not match. So it says it's half complementary. So this one matches, TA, AT, and so on. But here, let's say T faces C and so on, so they don't match. So again, there is nothing. Now this is the place to ask nanoparticle people, how would you guess that nothing happens?
Steric propulsion.
No. Right, but coagulation, these are nanoparticles, and they just stay in pairs. They don't really precipitate, right? So how would you guess that the nanoparticles coagulate or not?
Viscosity.
No. I mean, most people here should not know the answer, but I mean, like these two guys should.
Check the spectrum.
Right. Yeah. If you bring nanoparticles, the spectrum changes because they're close, and you can see the shift. So it's a spectral characteristics actually. There are some other methods, but in this case it's spectral. Now if you take exactly complementary target, so it zips them exactly it's supposed to be, you have high temperature for disassembling thing. So this is strong interaction. Now then you can start studying, say, okay, now I want to understand what's happened if the DNA does not match exactly. Now if you just take one here in the middle, no matching pair, you can immediately see that the temperature decreases quite a lot. It gets to be almost room temperature and is going to come apart. Now this is very fundamental, even more fundamental than this paper. This tells you exactly why DNA works so well in storing genetic information. Just one pair here actually decreases very strongly the traction. So for this reason, mutations and so on are really going to change the DNA interactions a lot. Just one mutation is already going to significantly affect the interaction between the DNA pairs, and supposedly the organism uses this in order to keep the information intact and so on.
So a 6-degree difference is enough to be.
It's significant in terms of energy. This means that it's much weaker in terms of interaction. Yes.
Why do interactions have to be parallel? Can they, like in the second in B part? Why do they have to be parallel?
You mean here? B.
Yeah. Like one chain can, like stick at many places. Or loop
right, but these chains are made in a way so if you turn one chain over, it won't stick. So they're made to actually stick to each other exactly in this configuration.
The one side does, but the other side, like the other chain, that's this.
This chain, you see, this chain is going. Okay. Oh, in this case, when they face each other, they're not going to face each other like in any way. There is no way in which they face each other, so they flip, they zip to each other.
No, but
No, I guess
they
she
don't
wants to know Polycarbonate form loops like a polymer.
Yeah,
does.
like loops.
Oh, like something like this?
No.
You mean why? Okay, like in reality, this is going
Yeah,
to be.
something like-
You see, in reality, this is going to be actually a spiral. It
No,
is
no.
going to be a loop.
Suppose if you have a surface with different A or B favored, and you have as in a polymer, as in a copolymer, some
Right.
part will stick here, and then there'll be a big
Exactly.
loop.
These are strands.
You mean the DNA goes back itself?
Yeah, so
Why
basically
can't-
the point is if
Uh-huh.
only the first 3 base pairs matches, so they stick. The next 3 base pair does not, they go
Right.
outside.
But that would
But
still be a
next week
very
again-
weak interaction. I mean,
Yeah.
I
It is
feel
going to
like-
be very weak. The point is the DNA also is not that flexible on that scale.
Hindrance, yeah.
So it's kind of it's designed by nature, so it forms these spirals and so on. But you can't really have DNA sticking to each other in any configurations than the one you like them. It's going to stick in this linear type of configuration, and then it's going to follow in spiral. But you can't easily have, let's say, DNA sticking like that and then going out. If we had that, I mean, our life would be much shorter and miserable. Because this is, I mean, essentially the fact that the DNA matches so well. And only when it matches, then that's when it gets kind of assembled and in this helical configuration. This is actually what's used by nature to correct mistakes. There are enzymes, and if they sense that the DNA pairs don't match, I mean, they would be cut and replaced and so on. So DNA is a unique structure. It's very useful in nature, and it's useful in research. It's maybe not that useful as people claim to be in nanoscale engineering because it's expensive, but you can do lots of things with it. So then, what is shown here is one base deletion. So eventually, in this case, the removed pair is here. Just one base is removed there. Now, what happens in this case is, you see, like here, this is sticking right in the middle of the chain, and it really kind of disturbs the chain. In this case, it's because it's here on the end. It's not a matter of non-complementarity. It's a matter just you don't have one pair. You have just one less pair binding. And you can see that actually in this case the melting temperature is about the same as this one. It's a very small decrease. And again, like the difference between this and this is very fundamental. So if DNA matches, even if it's shorter, it's still going to match strongly. If it mismatches, however, then the interaction becomes suddenly weak.
So have they done the other way around, having a mismatch near the end?
Mismatch here.
Yeah.
You can check in the paper. I think there was. I think I removed one because there were too many.
Or like it's just because of the mismatch that it drops so much.
In this case, it dropped so much because of the mismatch.
No, but if the
the
mismatch
idea of the
was near
mismatch
the
here.
end, yeah.
I think they have done mismatch here, and again it dropped significantly.
It would be interesting to see if,
So
if,
mismatch is much worse than a lack of pair,
if they put,
lack of base.
if they just threw
So
in
it
two
doesn't want to
mismatches,
bend.
just to see if what 2 mismatches. would
Right, it
accomplish.
doesn't want to bend, and it actually repels when they don't match. And then there is this case of one base insertion, so this one doesn't exactly match here. There is this base which is free. And you can see that this also leads to significant decrease. You can see that if you remove one at the end, the interaction is relatively strong, a little bit weaker but strong. But if you have this kind of defect in the middle, again the interaction drops not so much as a mismatch, but significantly. And this again, you can attribute this to the DNA, to the biological function of DNA. Any defect in the DNA matching is problematic. Now, nature may leave some DNA unassembled because in nature some protein would come and assemble it. But any mismatch in the middle of the chain, which is supposed to be already matching, immediately decreases the energy a lot.
So you can easily control the distance of separation between these particles just by controlling
Sure.
the type of DNA.
This is the idea. This is why the DNA can be used as a very specific, very good glue for anything. And these are just some of the ideas that you can do. You can put DNA on a larger particle and then put small particles around. Or you can have different nanoparticles modified with different DNA segments, and then you're looking for some specific DNA segment, like shown here, toxin. So how do you find anthrax? I mean, it's not that easy, straightforward. But if you eventually express the DNA, usually you use PCR, so you have lots of DNA. And then you mix it with nanoparticles, which can bind specifically to this anthrax gene. So then you see the nanoparticles aggregating, changing color, and so on, precipitating. And you know that you have this anthrax problematic kind of, you have the anthrax gene there.
This is Dr. Chad Merkin?
This is Merkin's research. And then Chad Merkin actually copied our method for electrical detection, about which I'm going to speak after the electrophoresis, and used the similar method to attach metallic nanoparticles and short circuit electrodes in order to do this detection electrically. But you can see that you can make a variety of structures just by using DNA. It's fairly simple. Now, this is one good use of DNA. There are some DNA computing research and so on, which I find to be kind of, I mean, like...
Yeah, but it's really cool.
This one?
No, the computers.
The DNA computing? Yeah, it's cool, but I mean, the idea about DNA computing, again, the idea about DNA computing is like that. If you program DNA strands, and instead of trying to make something combinatorial, let's say you want to figure out how different things match. Now, let's say you want to, for example, optimize all flights in the United States, and it's very difficult because a computer has to kind of move them all around and find which flights match well and so on in times. Now, the idea is that if you program in DNA and mix it, the DNA, because it optimizes the interaction, is going to flip in a way, so it's going to stick in a way, so you can then follow the DNA strand and kind of like follow the flights, for example, by self-optimization. This is a very cool idea, but it's practically useless in my view. Maybe I'm wrong, but I don't see much of application for that. On the other hand, however, applications of DNA in sensing, detection, and so on is great. And we're going to actually understand how this is done technically towards the end of the class, when we study microfluidics and bioarrays. If you have been to this seminar, the last seminar, departmental seminar, you have all those colored arrays and so on. All of them are made on binding of complementary DNA strands. Okay, and finally, again, like in terms of something that's interesting, maybe not that useful, the so-called DNA electrical connections with DNA. This is when you have the idea is very simple. You take two metallic electrodes. You attach a DNA strands on the two electrodes. Now then what you can do is you can take a DNA fragment which is going to bind here and here, and in a way form a bridge between the electrodes. Now once it forms this bridge, this electrical connection, now this is not an electrical connection, DNA is not a conductor by any means. Luckily, DNA can bind silver ions. When it binds silver ions, the silver ions can serve as site for silver deposition if you put silver, the so-called silver enhancer, essentially the equivalent of photographic developer. It deposits silver if you have silver ions someplace. So then this silver is going to get deposited on top of the DNA, and you can have this. You eventually have this strand. This is you cannot see the DNA here. You can see the deposited metallic particles on top of the DNA. But the point is, with some simple applications of DNA, you can make DNA connections on chips and so on. We were a little bit distraught by this research because it superseded just by not that much our research on sensors. But this is interesting, and of course, I don't say that this is going to be practical. But again, in terms of nanoscale engineering, things like that are what you want to in order to assemble microscopic and nanoscopic structures. Yes, Ken? Huh? Sorry?
We should try this in my.
You want to try this in your? This is another lens scale, Kevin.
Coating directly with DNA, coat DNA with, like, first coat the DNA with silver, and then form wires out of it.
Okay, I see that you're excited, but we can discuss this later. He was first, sorry.
What's the size scale of that image?
Actually, what you can see here, this micrometers. So this is 0 to 1.5 micrometers. So this length is 1 micrometer.
So this is a 0.2 micron wire?
Yeah, about so. It can be thicker, it can be thinner, depending on how much metal you deposit on that. It's not a real wire in the sense that it's more semiconductor or nonlinear properties than conducting. And the reason for that is because these are particles, and then there is some stuff around in the gaps and so on. So it's not really a good conductor.
Can you scale that down now?
In principle, yeah. In principle, perhaps. But again, if you scale this down, this means making it thinner, so you won't deposit much metal. And the conductance is going to be even lower. But in principle, you can. I mean, this is the motivation. Otherwise, nobody is going to make.
Yeah, you would make it with lithography.
Right. So the idea is that principally you can scale this down. And what I found more interesting is thinking about structures like that, but instead of just having electrical connections, and this is related to the research that I've done before, and which some of the students now will be doing, like Shalini, you can think about imparting electrical functionality on this connection when you have some specific binding event. It's not that you just connect them, but you connect them just when you have, let's say, specific DNA stress. Now you can say that this can actually work as a sensor if you like, because if you make that, and if this is the anthrax strain, and if it binds here, and then if you metallize it, it's going to make a connection. But that is not a practical sensing process. There are better processes than that. But, I mean, again, there is lots of coolness factor here, and there are lots of nanoscale applications which you can think of. I mean, this is really, again, I'm going to come up to this as a conclusion, but this is really a very rough and very early investigation of an area which has enormous potential for doing interesting and important things.
What are the two strands on the electrodes in the first diagram?
Here, these are two DNA strands. They may be the same or they may be different, which are attacked by using, again, SH thiochemistry.
Attached to the electrode?
To the electrodes. And they're made very simple. Eventually, you, like you would like to separate the electrodes perhaps, but you make a DNA, you attach SH groups at the end of the DNA.
They can't do that. There's like hundreds of DNA strands on each electrode, right?
Right.
Okay.
Yeah. Well, in principle, one attaches, and then once it attaches, I mean, like you see, like you don't see the DNA here. What you see here is the metal that's deposited.
Why don't we see a bunch of metal with all the strands?
Because they would like to have only one connection and show that they can make one connection.
How can they make just one?
So they just took a picture.
It's a trial and error process.
You just get lucky, essentially get
Right.
too close.
Yeah, it's a trial and error process. You just put a very small amount of the strands in the middle, and you try it a few times, and you're going to find this out happening.
Well, you measure the current first.
Yeah, they measure the current, the voltage, and
And once you see it connected, then you go.
it's not that good. I mean, it's not ohmic.
Just run the end.
You gotta run that.
Yeah. Well, I mean, there are people who do nanostructures by FM, and we're going to study them later. You can actually make a microwire by FM, but that's, I mean, it's again like more cute than practical. Again, I don't say that this is impractical. This in itself is impractical. There are very important practical applications. They may not build computer chips though. I guess kind of again when it comes to photolithography, especially with today's sub-100 nanometer photolithography, making a bridge of this size is not a problem for photolithography at all. But some applications like sensing, small nanostructures, what assemble of materials can be quite interesting in that respect. Let me show a few more cute things which are not related to DNA but to proteins. Now what happens if you take this molecule which has two specific small molecules at the end? Now what is this molecule here? This one. Somebody remembers from the previous lecture?
Avidin?
No, avidin is the protein. This is biotin.
Oh.
So this is biotin. This is phenylamine, nitrophenylamine, nitroamine, which is, you can find eventually antibodies for that. So you put antibodies on the surface of, let's say, gold particles, and you can use this as a bridge between the antibodies. So the antibodies lock on the two sides, and then they lock the particles in. Now, well, you can say eventually if you make it asymmetric, and let's say you take gold particles and silver particles, this is what these people have done. Stephen Mann, he's a good friend of mine in Bristol. You can put antibody here. One antibody is an antibody for biotin, the other one is for nitrophenylamine. So the gold particles lock to the silver particles, and you have gold-silver particle structure. It is cute as an idea, but then if you do the experiment in reality, this is what you get. It's not like here you have this nice organization and so on. They just precipitate quite strongly. So you have the tool, you don't have yet this nice structure that you would like to get. Again, this illustrates that you have an enormous power of making nanostructures, and this power is not being used yet because people don't know how to use it. And there are ways, for example, to make such nanoparticles, let's say gold, silver, nanoparticle arrays and so on, in a much better way. This is what nanoscale research these days is.
Excuse me. How strong are the antibody, like this?
Quite strong. In this case, quite strong. The moment they find what they would like to lock on, they lock on and clip strongly. It's lock and key. You have to watch the previous lecture.
Yeah.
But lock and key interactions can be as strong as chemical bond. And let me give you an example of even more complex. This is an example of how complex it can get if you want to and if you understand it. This research is done at University of Pennsylvania very recently. Amy was an outstanding graduate student in the group of Dan Hammer. So what they did was they take two types of particles. So they put on this particle, they put streptavidin. On this particle, they put protein A, which binds immunoglobulin. Then, on this particle, they put this molecule, which on one side has biotin, which anchors the molecule to this particle. On the other side, it has, these are actually polysaccharides, which are again part of the immunospecific system in the organism, but in this case, they have been extracted. So they put this chain with polysaccharides. And then here they put immunoglobulin, which specifically binds to these polysaccharides. And the binding of this immunoglobulin, actually, this is the E-selectin, is dependent on the concentration of calcium ions. So it binds only when there are calcium ions in the suspension. So you can control the binding and unbinding by controlling the amount of calcium ions. Now, how do you control the amount of calcium ions? This is a question for chemistry students. In solution, what is the easiest way to control calcium ions?
Just add some carbonate in there.
Nah. But it's close. You add chelators. EDTA. So it binds. It complexes the calcium ions. So you don't have to really do some change. You just add EDTA and calcium, and depending on the ratio, you have free calcium or not. But the point is that they have developed, so you can see now you start with one particle with biospecific group. You attach another biospecific molecule. You have another particle, you attach immunomolecule, immunoglobulin, and then you can control the interaction between two particles by controlling the concentration of a single simple divalent ion. And the structures that they get, this is just an example of cute structures, not as cute as nanoscale engineering. This is just changing by the concentration of small particles to large particles. So if you have a large amount of small particles, they call this micelle, they form a shell around the large particle. If you start increasing the concentration of the large particles, then you have these structures, and eventually when they go at a ratio of 1 to 2, the large particles organize themselves into this kind of chains and so on, because there is only one small particle to bind two large particles. And the reason this is possible is because you have biospecific binding. You can take oppositely charged particles and do that. Just because you control the interaction, so they kind of bind slowly and so on, they form these chains. These particles are now, the small particles are 1 micrometer and the large particles are 5 micrometers in diameter. So this is enormous, like from the viewpoint of DNA. And Amy was actually very interested in the biosensor research, and this illustrates the importance of multidisciplinary research. She would love to use these structures in electrical devices. But unfortunately, she didn't know electrical engineering then. So that's why really where you can have somebody with electrical engineering background actually kind of apply these structures in self-assembling electrical circuits, for example. Again, what I want to point out here is that I mean, you can use this as a building block. I put this molecule, then I put that molecule on it. I can control the interaction here and so on. And the structures that you make these days are so rough compared to what you could make eventually by really designing this and engineering this. Lots of potential there. Not that cheap, but certainly there is lots of potential of making such structures. Okay, our time is about up. This is the last slide. If you have any questions or something like that. There is quite a bit of ongoing research, not that much yet, as you see in the future, but this is an interesting area. So certainly keep an eye on that. Okay, let's finish then for now. Again, we don't have, this is for distance education. Next week is spring break week, so we're not going to have lectures then. But we're going to come back to theory for 2 more lectures. We have to take 2 more theoretical lectures. And this is electrophoresis and dielectrophoresis, the application of external fields to colloidal systems. And then we're going to go through a variety of applications to practice and high technology. Yes, Shalini?
Do AG+ molecules also like attach themselves readily to protein molecules or just the DNA?
Which one was
AG+,
molecule?
like Ag silver.
Silver particles.
Yeah.
Well, I mean, in order to do attachment to gold or silver, you have to have specific functionality at the end of the process. Now, you can attach proteins in 2 ways to gold or silver nanoparticles. One is to gold nanoparticles by using thiol groups, and then bind with the thiol group specifically to the gold nanoparticles. The other one is if you take proteins and you mix them with gold nanoparticles, they're going to bind to the gold nanoparticles because of hydrophobic attraction. Metal surfaces are actually quite hydrophobic, and any protein or hydrophobic molecules or surfactants are going to absorb quite well.
Is that stronger than the thiols?
No, it's not stronger than the thiols, and the worst thing is that also the protein molecule, the protein molecule, you can attach it by a thiol like that, specifically. So let's say this is your pocket. If you attach it with a thiol, the pocket is going to face outwards. If you just let it flop and absorb, it may absorb in any configuration, and your activity is going to go way down, which happens quite often actually. But again, you can think of the structures that you can make in this way. Okay, time is up. Let's finish, and you can ask questions if you like, just by coming here.